So here is my lockdown astronomy adventures. To be honest, I probably would have done this even if I wasn't in lockdown. I don't know why I put lockdown in the title, if I'm honest about it. Maybe it was because of the fact I'm working at home and therefore didn't have to get up at 6 o'clock every morning to go to work. Therefore, I was able to stay up till 3 or 4 in the morning to do this stuff. It might have been that. Maybe it was that. Let's go with that. Yeah. So it started off, yeah, right, okay. Nothing to do with what I'm talking about. I've been biking to Druridge Bay quite a lot recently. I just thought you should look out for this because it seems to be like as we get better weather, you notice this. I don't know if anybody knows what I'm actually looking at here. Anybody want to have a guess? Like type into the chat what you think I'm going to illustrate with this picture. What's going on in this picture that's astronomical? Oh, well done, Davey. Yeah, Paul as well. Yeah, this might seem like nothing, but every time I see it, it just brings home to me the fact that we're living on a planet. So in this picture, the purple region just between, like above the horizon and between the blue sky, that purple region, when I was down at the beach, sunset had just happened, and therefore what you're seeing when you see that purple region there is the shadow of the Earth in the atmosphere of the Earth. So you've got the red above it, which, like, if you were there, like floating in the sky in the red bit, you'd see sunset if you were looking towards the west. In that purple bit, you're actually in the shadow. So I'm going to ruin this picture by drawing on it, I think. So let me just annotate this. So it's like you've got the Earth, okay, and there's like a hazy atmosphere surrounding the Earth, very much exaggerated. If the sun is over kind of like in this direction, so sunlight's coming in from this direction, okay, there's the shadow of the Earth, and you're kind of looking at this region here. So if you're standing like there, can I draw people? There we go. Your horizon is there. You see this reddy region here and this purple bit here, which is the Earth's shadow. It's every time I see it, I think, oh, we're living on a planet. It's like, I know it's really trivial, but, and also it's called the belt of Venus. I've not been able to figure out why. If anybody knows the answer to that, I'd be interested to hear it. I don't know what the etymology of that is, but it's called the belt of Venus. So look out for it. You get it at sunrise as well, just before sunrise, but most people would notice it just, you know, the minute or two after sunset, and it gets higher into the sky, and it sort of, the effect disappears after a few minutes. But that purple bit is the Earth's shadow. Okay. Right. Okay. Let's move on. So I sort of had a plan at the start of the year about things that I wanted to do. One of them was like a really obscure thing, not a pretty picture at all, but it was to track down and photograph a Kuiper belt object. I'll get to what that is shortly, okay? I also wanted to do a bit more like serious astronomy stuff, not just like take pretty pictures of things. I wanted to do some spectroscopy, and I talked about that in the previous time I talked, so I don't really want to go into all the detail of that again, but I did get a spectrum of a nova. I got 3 or 4 actually in the clear nights that we had, so I've put a picture of that there. Okay, we'll talk about spectra a little bit more later in the context of quasars. Having said all that, I did want to get some pretty pictures of galaxies as well, because you know, astrophotography is something I do enjoy. I do think it's more art than science, but other people might disagree with that. But at the heart of all this, at the start of the year, my telescope wasn't working. So like all of this was in jeopardy. Not the telescope was fine. The mount was not working, and I knew I'd have to deal with it. So let me just kind of like take you back to the start of the year for me, okay? When I was going out trying to attempt to take pictures, roughly half to 3/4 of my individual pictures turned out like this, with little comets in them, okay? So not pinpoint stars, I was getting shapes like that. So that's where the mount is tracking for a little bit, and then it slips, and you get this trail, and then it tracks okay for a little bit longer, then it slips again. And roughly half to 3/4 of the pictures I was taking, I was having to throw out before I even start processing them. So that wasn't good. It meant that I couldn't take pictures of like Mars because Mars wouldn't stay in the frame for long enough. It was just horrible. It got to the point where I knew I was going to have to deal with it. I would have to go inside the mount, figure out what was going on and fix it. And I'm not a practical person, okay, and that terrified me. So I was on YouTube looking at videos about how to do it. And this was it. I mean, like opening a telescope, honestly, I'd rather probably like remove my own appendix. I'd be more confident doing that than going into this thing and messing around with the gears. So I forced myself to do it because I knew like it wasn't a clear sky, so I wasn't going to be missing anything anyway. So the picture on the left is my actual telescope. The picture on the right is how far I thought I would have to go to get this thing fixed. In the end, I didn't have to do that. I had to remove a few more panels. I had to mesh the gears a little bit better. There was quite a lot of backlash in some of the gears. I mean, the whole point of the mount is, as the Earth turns, the stars move across the sky. Your mount compensates, and it's got to track the stars precisely while your camera shutter is open, letting the light in, and it just wasn't doing that at all. So, to cut a long story short, after a lot of like messing around and a bit in the middle where I thought I'd totally destroyed the mount, I managed to get it back together again. And when I tried it again, it wasn't perfect, but it was, I would say it was back to about 95% working well. So I thought I'm not going to touch it again after that. I've had it for 10 years. Hopefully it'll last another 10 years without me interfering with it. So I'm ready to go. I'm ready to do my project now. That was one of the first pictures I took after I'd fixed it. So this is, I'm sure it's familiar to a lot of people here. These are two galaxies in Ursa Major. We've got M81 on the left, M82 on the right. These are a pair of interacting galaxies about 12 million light years away. And it's galaxy season at the moment. So I want to tell you what that means and kind of like, you know, why do we have a galaxy season? Anyway, lots of galaxy pictures, lots and lots of galaxy pictures at this point. So virtually every clear night I was out taking pictures. Okay, so this is the Draco triplet. Somebody on Twitter told me that the nickname for this is the sampler, and I didn't get it, but apparently it's because you've got a sample of a spiral galaxy, an elliptical galaxy, and what's that one? I think that there's two spiral galaxies there. There's a bad spiral, a normal spiral, and an elliptical one in the middle. So you're sampling all the possible kinds of galaxies. I'd never heard of that. The guy might have just made it up on the spot. I wouldn't know, to be honest. There are lots and lots of galaxies at this time of the year. This is the Leo triplet. It's a much more famous group of galaxies in the constellation Leo. Oh, just every clear night. I mean, we've had some really cold, clear nights, and I've been out just snapping away, and it's mostly galaxies. So the one on the left is M60, and it's another interacting pair of galaxies in Virgo. The one at the top is M81 again. The one next to it is the Whirlpool, M51. Below that one, we've got, this is M64, nicknamed the Black Eye Galaxy. And this is M63, which is nicknamed the Sunflower Galaxy. The M's, in case you're not familiar with them, are named after a guy called Charles Messier, who either discovered these things or catalogued them a long time ago because he was interested in comets and he wanted to keep track of things which weren't comets. So a lot of these things have M numbers, and they're usually the brightest things you can see with the telescope. So quite often it's worth chasing them down. And a lot of them are galaxies, as you can see here. I was just on and on. We did eventually have a run of clear nights. NGC, the Fireworks Galaxy. NGC is New General Catalogue. That's the catalogue that came along after Messier and contains generally fainter things. But these two galaxies are very similar. It's just that one of them you're looking at from kind of like above or below. That's the face-on spiral galaxy. And the other one is Edgeways-on. And it's a spiral galaxy, but seen from a different perspective. So it's galaxy season. Did I mention that? This is in Virgo, and unbelievably, in that picture, there are several hundred galaxies. I mean, some of the big, bright, obvious ones they form a kind of chain down here. It sort of wraps around there, and it's called Macarian's chain, named after an astronomer called Macarian who was working in the 1940s. But elsewhere in that picture, I don't know if I zoom in and zoom, it's not going to let me zoom in. Okay. But a lot of the other dots in that picture as well are galaxies. This is part of the Virgo cluster of galaxies, which is just a massive collection of galaxies between about 50 to 60 million light years away. And again, at midnight, this part of the sky is high in the south. So the midnight side of the Earth is facing this part of the universe at this time of the year. So that's why it's galaxy season. This is a map to kind of illustrate our local universe. Okay, it's very hard to do like a 3D map of the universe in here, but if you look at the scale of this thing, it's about 100 million light years across, and our galaxy is at the center of this map. It's not in the center of anything really, but in this map, the Milky Way is in the middle, and we are part of something called the local group. Okay. The most famous member of the local group is the Andromeda galaxy, and there's a few others, okay, big ones like the Magellanic Clouds from the southern hemisphere. There's the Triangulum galaxy, but there's about like 40 to 50 galaxies in the local group. So at this time of the year, this direction is the way that the Earth is facing at midnight, and we're looking towards this massive galaxies here called the Virgo cluster. And there happens to be a few others along that line of sight as well, notably the Ursa Major group, loads of galaxies near the Plough in the sky, and the Coma cluster as well. So there are thousands of galaxies within the reach of like our telescopes. Okay, so that's galaxy season. And as the Earth goes around the sun, in a few months' time, midnight in the sky will be kind of like in that direction. We won't be pointed in the direction of these galaxy clusters anymore. So galaxy season is very well defined. It's sort of January to April every year. So we're coming to the end of it. As part of this, I thought it was interesting to show you this. To take a picture of a galaxy, you have to take a series of images. So for that spiral galaxy, I pointed the telescope and the camera at the galaxy, and I took roughly 2 hours of exposures. And when you combine those 2 hours of exposures, there's usually, well, in my case, there was about 40 of them. You kind of stack them together in special software, and there are kind of algorithms which will remove artifacts from the image which shouldn't be there. So, for example, if you think of like a pixel in that part of the picture there, that's just like empty space, okay? So on average, those pixels will be dark. If a satellite happens to drag through your picture, in one of the images, you'll have pixels which are very bright, but the rest of them are very dark. So you can get the software to say, well, anything that's very bright here, remove it in the final result. And in that way, you usually get rid of a lot of satellite trails. The technical term is sigma clipping or median filtering, okay? But the software usually does it for you. You don't need to think about it. I just thought, when I was looking through all the raw images for this picture, it astounded me how many satellites were just traveling through the picture. And this is mostly thanks to Elon Musk and his Starlink constellation. I read somewhere recently that between like 1957, the start of the space age, and last year, there were something like 4,000 or 5,000 satellites launched, and some of them are still up there. Some of them have come back through the atmosphere. Elon Musk and his Starlink constellation will put up 42,000 new satellites over the next few years. And he's not in this game alone. There are competitors who are also launching mega constellations. This will drastically change our night sky. Even kind of like painting them black doesn't seem to kind of mitigate that much against the brightness of these things. So at the moment, we can filter this stuff out, but every time you filter an image, you lose a bit of the good stuff. You lose some of your actual data along with the satellite trail. So it's not like harmless. And professional astronomers are more worried about it than like me. I'm just like annoyed that I have to filter this stuff out of my images. But professional astronomers studying exoplanets, for example, they need no change in their images. They need to be able to see the thing they're looking at and guarantee nothing's going to pass through the image. But with 42,000 new pieces of junk up there, sorry, satellites, that's going to be increasingly more difficult. Anyway, there you go. So I wanted to track down some Kuiper belt objects. That was one of my objectives for early this year. So the Kuiper belt, I want to kind of like tell you the story of what it is. So if we go back a few centuries, the solar system, up until a few hundred years ago, used to be thought of as being the sun, the Earth, and 5 other planets. Okay, and that's what the picture represents here. Beyond the planets, you had the celestial sphere, which has the stars. And after the telescope was invented, we gradually began finding more distant planets, planets which were too faint to be seen with the naked eye. So the planet Uranus was discovered by telescope in 1781. There was an apparent gap between Mars and Jupiter, and astronomers began searching the sky for faint stuff moving through these constellations, which had orbits between Mars and Jupiter. And the first minor planet was discovered in 1801. It's called Sirius. Lots of other minor planets, which were later called asteroids, were discovered after that. Planet Neptune was picked up in 1846. It's visible with binoculars, but at the time it was the result of a careful search again after the discovery of the planet Uranus. So you got Neptune, and then finally Pluto was added to the tally in 1930. The search for Pluto was inspired by the fact that people thought Neptune was deviating from its predicted path, and they thought that maybe there was another planet beyond Neptune pulling it off course with its gravity. So a search for Pluto was set up, and within a couple of years, Pluto was discovered. But it turned out to be really unusual. So I'll get to that in a moment. So certainly the solar system, as I grew up with it, had 9 planets in it until 2006, when things began to change. So this is the sort of picture in astronomy books that I would see as I was growing up. 9 planets, there's Pluto. You've got the sun, you've got the asteroid belt, and you've got comets, okay? So this is how things used to be. Pluto, almost as soon as it was discovered, turned out to be different. The orbit, as you can see in the picture, takes it like, well, it's not even close to circular. It's very elliptical. Sometimes it's very far from the sun. Other times it's a lot closer. In the picture, it looks like it intersects with the orbit of Neptune, but it doesn't really. If you were to spin it around and look at it, they never really get close to each other at all, but it's tilted at a big angle. When things are different like that, it indicates that the origin is different. So Pluto was unlikely to have formed in the same manner as the other planets. Okay, so the orbit of Pluto, the size of Pluto, eventually we worked out that Pluto was actually smaller than our moon, and totally different to the gas giants that are out there, Jupiter, Saturn, Uranus, and Neptune. So Pluto was very different. We've known this for decades now, but it could probably still be called a planet. Okay. Now, along with this, astronomers are studying comets as well. There's a picture from last year. I hope everyone got the opportunity to see Comet Neowise. There might be another bright comet coming in December. More about that nearer the time, maybe. Now, comets orbit the sun, and astronomers, they like classifying things. They classify the orbits into basically 2 types. You've got short period comets, which take less than 200 years to go around the sun. They tend to be comets which orbit in the same direction as the planets revolve around the sun. Okay, so it's not just the period, it's actually the direction they orbit. And their orbits are not tilted that much in the same way as Pluto. They tend to be very kind of like shallow angles to the orbits of the planets. The other kind of comet, of which Neowise was one last year, are long period comets. Now, as well as being long period, they also have orbits which seem to be randomly tilted around the sun. So some of them are above and below the plane of the planet's orbits, and others come in from this direction, and some kind of like do that. They're not kind of going around in the same direction as the other comets, and that suggests that these are two different populations and their origins are different. So astronomers wanted to figure out what was going on with that. Why do we have short period? Why do we have these long period populations? So back in the 1930s and 40s, the speculation was, when you study the short period comets, 200 years, okay? Now 200 years is roughly the time it takes Neptune to go around the sun. So these comets have paths which take them a little bit beyond Neptune and then back into the sun again, okay? Some of the comets which have shorter periods, so for example, Comet Encke has a period of 3 years. We think a comet like that probably started out having a period of about 200 years before it passed too close to a planet, like maybe Jupiter. And then Jupiter changes the orbit of this comet into a new period. But most comets end up out there beyond Neptune. So because some comets eventually fizzle out as they run out of their volatile material, or Jupiter kicks them out of the solar system, or they crash into a planet, they need to be replenished over time. Okay, the solar system is billions of years old, and we think comets maybe last a few million years. So if they're not being replenished, then we wouldn't see comets these days. So the source of replenishment was speculated to be a reservoir beyond the orbit of Neptune. And the idea was that if Neptune orbits on the inside of this zone, occasionally its gravity is going to change the orbit of one of these objects so that it falls in towards the sun and becomes a comet. Back in the 1930s and 40s, there was absolutely no evidence, no direct evidence for anything beyond Neptune apart from Pluto. And that remained the case until 1992. As you get into the latter stages of the 20th century, you've got CCD detectors, you've got incredibly sensitive cameras, bigger telescopes, and we're now able to explore this region beyond Neptune. And the first trans-Neptunian object was discovered. In the years since, this is how a map of the solar system looks. And this is the most up-to-date one I could find in 2017. The only thing that would be different in 2021 is that there are more objects on it now. So just orient yourself with that map. You've got the orbits of the outer planets there, and beyond Neptune, you can see there's a whole population of newly discovered objects. So all of these were picked up since 1992, and there's more than 1,000 of them that we know about out there. And Pluto is in amongst them. It looks like Pluto is just the biggest member of this group. Okay, so this zone, which was postulated by Gerhard Kuiper in the 1950s, is now called the Kuiper Belt. So these are tiny icy objects, probably similar to Pluto, some of them probably different, but they're beyond the edge of the orbit of Neptune. Just for completeness, the long period comets come from much, much further out. So another astronomer called Jan Oort, he speculated that the origin of these comets must be similar to the Kuiper Belt. Okay, so for them to basically fall in from any direction, we must be surrounded by a shell of comets at a very great distance from the sun. And these comets within this shell are actually disturbed by the passage of other stars, because this thing is vast. This thing might extend outwards to almost the nearest star beyond the sun, 2 light years out. So as the sun moves through the Milky Way and other stars disturb this thing, they begin a 5 to 10 million year fall into the solar system. And then it becomes a comet like Neowise that we see in our sky. And then it heads back out again over a journey which lasts just as long. Anyway, there we go. So we've got this list of Kuiper Belt objects now. These are the biggest ones. Now, if you look at this, Pluto is on there, but can you tell immediately whether it's the biggest? It's not obvious. Eris looks roughly the same size next to it. So Pluto is just one of a population. So in the minds of some astronomers, is it even right that Pluto is now a planet? Is it not just like a Kuiper Belt object, but maybe the biggest one? I don't know if you've got like really strong opinions on this or not. Certainly it was a thing in the past. In 2006, it was a big thing. But look at all the others. So the names of these things tend not to come from Greek mythology. They come from the cultures and mythologies of other people. So Inuit mythology is represented in here as well. Hawaiian mythology and lots of others are now, I mean, there just aren't enough names in Greek mythology for all these new objects. So either Pluto is a planet, in which case, why isn't Eris a planet? Or if Pluto isn't a planet, what should it be? I mean, what are these anyway? So my goal was to take pictures of some of these, if possible. Yeah, so look, chasing Kuiper Belt objects. Pluto is the brightest, but it's too far south and it's the wrong time of the year to see it. Okay, so I'm probably going to try for a picture of Pluto in the next few weeks, if not the autumn. But these other ones, Haumea and Markea, they're nice and high in the sky this spring. If you're interested, they're in the constellation Bootes, not far from Arcturus, the brightest star in the northern sky. But it's faint. These things are 30 times fainter than Pluto. But anyway, I looked up where it would be, and I took a picture, hoping against hope I would find it. And I did. I got it. I got Haumea. So this was my first Kuiper Belt object, 7.7 billion kilometers from Earth. Can you see the little thing jumping in between the pictures? I'm hoping like the compression isn't utterly ruining this. Can you see it? Give me a thumbs up if you can see it. Thanks. Right, okay. The pictures were taken just over 24 hours apart. So Haumea moved around the sun a little bit, but mostly it's the Earth that moved around the sun. It's the Earth's movement which makes Haumea move in this picture. So that was good. Markea was about the same distance, about the same brightness. So I had a shot at that. It's not an animation, this one. I was so not confident I would get it. I actually didn't bother going out the second night to take a second picture. And when it turned up in the first one, I was a little bit gutted not to have tried this, but it was there. Okay, so this is Markea, another Kuiper Belt object, 7.7 billion kilometers from Earth. Now, at the same time, I was reading on Twitter, some of the people, my friends on Twitter who I follow, were also trying the same thing. So we kind of like came up with an idea. Actually, I didn't. It was this guy called Rob Tilsley. He was chasing these things as well. And we decided to pool our images to try and track the Kuiper Belt object over a couple of weeks. So it's not a great animation here. I tried to enhance it a little bit so you can see. So my images are in there, and we've got over a period of a couple of weeks, Markea moving against the background stars. So that was a nice collaboration on Twitter. And it just happened completely accidentally. So, you know, Twitter can be a bit of a cesspit at times. I'll not lie to you about that, but it depends who you follow, doesn't it? So that was quite nice. I'm just checking the chat. I'll come back to your question at the end, Ian, if that's all right. Now, right, okay. So look, this is like me learning how to figure out stuff about my kit as well as anything else. So in my picture of Markea, I noticed there were some fuzzy blobs in there as well. So I was curious to see what they were. Okay, so I've zoomed in a little bit on my picture. And the fuzzy thing, the one with the circle around it, is a galaxy. And when I looked it up in the LIDAR catalog, it turned out to be 1.1 billion light years away. Now, as we heard in the lecture last time, there's different measures of distance. Fred Stevenson told us about like look back time, and there's how far it is now in the universe in the time that it's taken the light to get here. So I'm talking about look back time. So the light from this galaxy has been traveling 1.1 billion years before it reached my camera. Looking even more closely, barely registering at 3.3 billion light years was a quasar. with that catalog name, which I'm not going to read out. And just barely, I don't even know if you can make this out here, but right at the end of the arrow here, 4.4 billion light years away is another quasar. When I was younger, and I used to get Astronomy Now, I think in one of the very first editions of Astronomy Now, they mentioned the discovery of a quasar with an extremely high redshift. And I remember not knowing at the time exactly what redshift meant, but that the number was 4.5. And that was with like one of the biggest telescopes in the world. Well, my kind of like 8-inch telescope has picked up something even further away than that. So this is like not the most amazing telescope on the planet, and it's able to see that far out into the universe. Another way of thinking about it, that light left the quasar maybe before the Earth was formed. So it left the quasar, then the sun and the Earth formed, and like, you know, a lot of stuff happened. And eventually I came along with my telescope and I was there ready for it. I was ready for it to collect the light. Anyway, it's amazing what you find. And this is just some random direction in the sky. Okay, so every direction you look, you'll find similar kinds of things. Anyway, that got me thinking, quasars. What else can I do with quasars? So I went on a bit of a quest. The picture that you can see there illustrates probably one of the most kind of interesting things about quasars. When you look at them, they look like stars, okay? Without the two little dots and with the thing being in the center, that would just look like a star. The thing that makes it different is that when astronomers began measuring the spectra of just about every star in the Milky Way that they could see, these things were really unusual because they had redshifts, which indicated that they were either extremely fast-moving stars in the Milky Way because they had a redshift, but then they all had redshift. So it's like every star that they picked out like this was zooming away through the Milky Way, away from us. That seemed very unlikely. The alternative was this was a cosmological redshift. The redshift was caused by the fact that the universe is expanding, and therefore, this isn't a star in the Milky Way. This is an extremely distant, powerful object at a very great distance, which is kind of being carried away by the expansion of the universe. This is one of the first ones to be discovered, and it goes by the name of 3C273, the 273rd object in the third Cambridge Atlas of bright radio sources. Okay, they were also called quasi-stellar objects, but obviously that's a bit of a mouthful, so the name quasar was kind of used to abbreviate that, so they became known as quasars. Now, the radio astronomers with radio telescopes who studied these things often found that they were less like star-like objects and they were more like extended, loud radio things. So the other name that they had was radio stars back in the early days. They emitted a lot of radio waves, some of them. Now, what it actually is, with the benefit of like everything we've learned in the last half a century, is that a quasar is a supermassive black hole surrounded by a disk of material. So this might be gas that is just spiraling in like water down a sink, okay? And as the gas spirals in, friction heats it up to very high temperatures and it begins to emit energy in the form of like X-rays, gamma rays, radio waves, right across the spectrum. So this is stuff falling into a black hole. These supermassive black holes, we think, have very intense magnetic fields, and some of the material doesn't fall directly in. It gets accelerated upwards and outwards by the magnetic field into these very long, precise collimated jets. These objects are probably amongst the most powerful luminous objects in the universe today. Looking up how much energy they put out, this thing puts out about 1,000 times more energy per second than the Milky Way does with all of its 100 billion stars per second. And the size of this thing compared to the size of a galaxy is tiny. This thing is bigger than our solar system, but the black hole in the middle would probably fit into kind of like the orbit of Neptune, okay? So compared to the size of the galaxy that it sits in, this thing is tiny, okay? But it's putting out more energy than 1,000 galaxies. And it's just because it's a black hole being fed with material. Now, a few years ago, we got our first direct image of a black hole. This is it. And again, there's a size comparison there to the solar system. So this is a supermassive black hole with the shadow of the event horizon surrounding it, which was imaged by the Event Horizon Telescope in 2017. So a quasar can be in the center of one of these galaxies, and there's actually a whole class of other objects apart from quasars, which this model explains. So if you view the black hole and its accretion disk from a certain angle, you see a quasar. And that's, if you're looking down the jet, you see a very bright quasar called a blazar, okay? And if you look at it from another angle, you see much less intense, and it just looks like a bright point of light at the center of a galaxy called a Seyfert galaxy. So all of these, what were thought to be different kinds of objects, have been unified under this same object. It's a black hole being fed. Now, 3C273, the one I took a picture of, looks like this through the Hubble Space Telescope. So that bright star-like object is the quasar, and you can't see the galaxy because the quasar is so bright. But if you mask the quasar inside the telescope, you put something in to block out just the quasar, you begin to see the light of the host galaxy around it. There's the fuzzy blur of the actual galaxy surrounding it. So this, I mean, they're just mind-blowing how powerful these things are. If you can hide an entire galaxy behind this thing. So here's my picture zoomed in, right? Now, I just thought, well, it's a picture of the quasar. When I looked a bit more carefully, look at this. Again, this is far too much time on PowerPoint. This is the Hubble Space Telescope view. So I've turned the image around to match mine. So just again, just to convince you, did I get the jet? There's a jet of material coming out. I'll remove it. I think it's there. I think I captured the jet from the supermassive black hole as well. This is 20 minutes of exposure time on the 8-inch telescope. It's there, just about. I'll probably try this again to see if I can get it a little bit better. This is a long way away. Do you know what? Do you know how far away this one is? Well, I thought I would measure it. My next project. How far, because you know what, you read about how they measure the distances to these things. I wondered if it would be possible for me to do this, so I decided to try. Now, before I get to that, quasars are just temporary features in galaxies. They're not thought to like persist for very long. So galaxies live for billions of years. A quasar might be active for just a fraction of that, like 1% of that time. And we've spotted a lot of interacting galaxies where quasars are also present. So if you've got galaxies colliding, that means you've got a lot of gas being fed into the central black holes of each galaxy, and that might switch on the quasar. Now, that makes me think that in the future, when the Andromeda Galaxy collides with our Milky Way, that might switch on the supermassive black hole at the center of our galaxy, and our galaxy might become home to a quasar eventually. It might have been one in the past, we don't know, okay, but it certainly might in the future. So my next project, how can I measure the redshift of a quasar? Because if you can measure the redshift, that means you're measuring the expansion of the universe. And I wanted to be able to say that I'd done that. Okay, so that was literally the reason for doing it. So I did it. I mentioned this in the previous presentation that I've got this diffraction grating. Well, here it is. This is the result of it. The way I did it was I measured the spectrum of a star in the Milky Way. I picked a star called Alderaan. It's not a particularly bright one, but it's a certain type of star with absorption lines that are quite strong. So if you look here, you might be able to make out these lines in the spectrum, okay, so that you've got some there. These lines are associated with hydrogen in the atmosphere of the star, and the hydrogen absorbs certain colors of light from the interior, and it gives these absorption features when you split the light into a spectrum. When I measured the quasar, okay, so as soon as I took that spectrum, I moved the telescope to the quasar. In the quasar, because it's a really energetic thing, the hydrogen isn't absorbing the light. It's actually shining so brightly and being heated to such an extreme that hydrogen is emitting light in the same places, in the same wavelengths. So we get the same pattern of lines, but this time they're emission lines, and they're shifted. So as soon as I kind of like saw that and began to measure it, I could match up the lines in our galaxy with the red shifted lines. They've moved that way in the picture. So how you measure the redshift is to measure exactly how much they've moved in terms of the wavelength of the light, okay? So this is the spectrum of the quasar, okay? And I've got 3 definite wavelength detections for hydrogen. I've got hydrogen alpha, beta, and gamma. And measuring where they are here, okay, so measuring the wavelength here and here and here, I know that compared to the rest wavelength on the Earth, they have moved by that much. So if I'll just demo one of the lines there, you can see the hydrogen alpha has moved that much that way, okay? Redshift is calculated by measuring how much it's moved, and there's a formula for it, okay? So it's not a maths lesson, but when you plug the numbers into the formula, it gives me a redshift of 0.158, okay? When I looked it up, it was 0.159. That was the professional kind of like estimate. So when I averaged the 3 of them, it came out as 0.158. But just the one of them, it's that little bit out. So that's a hit. That worked. So because we think this redshift is a consequence of the universe expanding, so the light's on its way to Earth, and as it's on its way to Earth on that billion-year journey, the universe expands and stretches it. Okay. The distance is from a formula, and when you plug the redshift, the speed of light, and how much we think the universe is expanding, which is h0, plug the numbers in, you get a distance of 2.2 billion light years. So the distance is taken directly from the spectrum that I measured. I've measured the expansion of the universe. I'm not relying on people saying, you know what, the universe is expanding. I've measured it. I have measured it and worked out the distance. So this is like, it's a really excellent feeling to sort of like be able to verify things that you've read about in books. And it's part of the beauty of science, I guess, that these results are reproducible by, in theory, by anybody with the equipment to do that. Right. Okay. This is trivial, but I thought you might like this. A couple of weeks ago, I knew the International Space Station was going to pass in front of the sun. There's a website where you can put in your coordinates, and it'll tell you in the next month whether you can expect to see the space station pass either in front of the sun or the moon. So on 16th of April, I was ready with my telescope. The space station zipped past the sun in an event which lasted just over half a second. So I was snapping away with pictures, and I managed to get a composite image of the space station. So this is a transit of the space station. If I'd been a little bit to the south, so I'm in Red Row, if I was in Widrington, I wouldn't have seen this. And if I was a few miles north, say in Amble, I probably would have missed it as well. So you've got to be in exactly the right place at the right time to watch for this. That website is really easy to use. You just put in your coordinates, your latitude and longitude, and it'll tell you what transits are coming up. You don't need a telescope to view the ones of the moon, because the space station can pass in front of the moon. You can watch it with binoculars, or it just looks good when you see the space station fly past the moon really quick. I got a moon one last year from the same website. So it was taken in daylight, and again, you can see the orientation of the space station was a little bit different. Okay, right. Anyway, that's kind of trivial, but it's a nice thing to do. When I checked today, there were no more for the next 4 weeks for me. Okay, but that's just if I'm not prepared to travel out of Red Row. So it's worth checking. You might get one. So the last thing I wanted to share with you was about exoplanets. My plan was, and I was really not confident that I'd be able to do this. It was to look for an exoplanet transit. So the background of this is that we've thought for a long time that there are planets orbiting other stars. And in fact, we discovered the first planet around another star back in 1992. In 1994, we added another one. But in the years since then, we've gotten very good at looking for planets around other stars. Now, it's not easy, especially like a couple of decades ago, because stars are extremely bright objects, okay? So Mark, you might recognize this. Kathy, this is your picture, I think, isn't it? The Milky Way has 100 billion stars, more or less, in it. So if you think about, like, for example, that star there, okay? If you just look at that through a big telescope, what you see is a very bright version of the star. If it's got a planet, the planets are tiny in comparison. They reflect light from the star. They're not luminous. So looking for planets directly has been a major issue. So astronomers have traditionally settled on indirect methods of detecting planets around other stars. One of the first methods to be used successfully was, again, looking at the spectrum of the star. If a star has a planet orbiting around it, it might be that the planet is big enough to disturb the movement of the star. The star will actually trace out a little circle, and as the star comes towards you, the lines in the spectrum will be shifted towards the blue, and as the star moves away from you on this little circle, they will be red shifted. And if you can measure the periodic variation in those lines, you'll know there's a planet there, okay? So you can't see any of the planet, just the star and its spectrum, but you would know there's a planet there, okay? So this is called the radial velocity technique. The other method, which is really successful, is you could take a picture of a star and take lots and lots of pictures of a star. And if at some point the brightness of the star decreases and then increases again, you get a little dip in the brightness, and then that repeats periodically. That could be because of a planet as well. But these methods are very, very difficult to carry out, okay? The size of the dip might be dependent on the size of the planet. You could figure out a lot about the planet from the shape of the curve as it passes in front of the star, okay? So this is the transit method. Now, since I've mentioned those, it's worth pointing out that image processing telescopes have improved to the point now where we can actually begin to directly image some planets going around other stars. And if you monitor them over periods of years, you begin to see there are other solar systems out there. It's not just like us and our planets here. There are entire other solar systems out there. So this is a star a very long way from here, and we're kind of looking down on it from above or underneath it, perhaps, and we see the planets moving out along their orbits. The image processing has removed the glare of the star to just leave the planets circling around the star. So this is incredible. So we know we can use these methods as well. I can't, okay? This is way beyond anything I can do here, but the transit stuff, that was potentially doable. So just to finish the story off here, so far, all of our searches for planets in the Milky Way have been restricted to our neighborhood, okay? So we've searched for planets in a very restricted region of the Milky Way surrounding the sun, out to maybe like, actually now out to probably 1,000 to 2,000 light years. So we've expanded that a little bit, but it's still just a tiny patch of the Milky Way. Today, we knew about 4,375 exoplanets, okay? There are 5,900 candidates. That means we're waiting for them to pass in front of their star again. We're waiting for another detection, and then they can be confirmed, okay? And there are 3,247 planetary systems. So those are other solar systems, and there are probably a lot more. If you extrapolate that out to the whole Milky Way, if we assume we just live in a typical patch, it means that there are, on the scale of about 100 billion planets in the Milky Way. And if you've got like 1 out of 8 of them, maybe in Earth-like orbits around their stars, okay, it might be more, it might be less. The numbers suggest there might be like 40 to 50 billion similar to the Earth. Okay, it might be a lot less. It might be actually a lot more. We don't have a good handle on that yet. So there are everywhere. So I wanted to see if I could find one, or at least detect one. I don't think I'll discover one, but I could certainly try to chase one that's already been discovered. What really inspired me to do this again was Twitter. Twitter can be an awful place, but you know, there's a lot of positive stuff on there as well if you follow the right people. So there's a person I follow I think he's a student at the Open University called Phil Michel, And he detected an exoplanet earlier in the year. And I thought, well, if he can do it, I'm going to give it a try at least and see if I can do it. I just needed to find a candidate planet to try and find. So I wanted to do something easy, if there is such a thing. I wanted to find a star where the star would drop a lot in brightness during the eclipse, okay? And I didn't want it to last for like 6 or 10 hours. I wanted it to be done in an hour, hour and a half tops, okay? Because I thought, well, what are the chances that the sky is going to be clear for that long for a start? So I needed to kind of choose something easy, okay? My plan was find the star which has the predicted transit and then take pictures before, during, and after, and then see if I could use the software to do the search, okay? The only skills you need to do this are those which you probably already have if you do astrophotography, okay? So you need your images, but you also need to take darks, flats, and bias frames, okay? So without going into that, it just means the images that ensure your pictures contain only the data from the sky that you're interested in, okay? So this is Planet Hunter, okay? This is my telescope. That's the camera I used. Set up in the garden a couple of hours ago. So I used the 8-inch Meade. I've got a black and white mono camera. The big issue that I thought I would have was it's not cooled. Fortunately, the night I was out, the temperature dropped to -2, so that probably helped a bit. So the cooler the camera, the less like background noise you're going to get in your images, and that presumably will make the detection a bit easier. So this is how I did it. I found a candidate star. It was in the constellation Hercules. It has a really long catalogue name, but the short name for it is TRES 3, okay? It's 12th magnitude, okay, which makes it a little bit brighter than those Kuiper belt objects I was chasing, but it's definitely a very faint star. 760 light years away. It's a spectral class G star. It's basically the sun as seen from 760 light years away. This is a very sun-like star. The planet was discovered in 2007. It's a hot Jupiter. It's something which is 1.9 times the mass of Jupiter, and it orbits very, very close to the star, just 3 million kilometers from it. So if you think of Mercury, Mercury's like 58 million kilometers from the sun. This is a fraction of Mercury's distance from the sun. So it zips around its star every 1.3 days. That's a year on this planet. And the transit is expected to take 77 minutes. The depth, so the change in magnitude was expected to be a 2.5% fall. And that was a big drop for an exoplanet. Usually they're much, much smaller drops than that. And that's a picture I took on the night of the transit of the star. So you can see it's just a pretty nondescript star in the sky amongst many others. And finding it wasn't easy as well. So it took me about an hour to actually locate it and make sure it was in the center of the field of view. So look, I'm not a genius at this stuff. I know how to take pictures of normal things like galaxies. Unfortunately, that's all you need to be able to do. There is dedicated software called HOPS, and you just work your way through the menus on here. So you select your images. So that's your lights, your flats, your biases. You just feed everything in there. The reduction is where it just calibrates everything. So it does what like Deep Sky Stacker does, or whatever software you use, like PixInsight. The bit where you get involved is the inspection. So I wanted to show you what that looked like. So here's one of my monotone images. And that's the star in the middle of that picture. The graphs show you how the sky brightness changes. It's measuring the background of the sky, because this thing started off quite low in the sky, and that meant the sky was a little bit brighter because there's more atmosphere. But as it rose into the sky, the brightness of the sky fell. And the other bit of it is how big the star images are, because, like, you know, I haven't got perfect tracking on my mount. And sometimes the wind blows the telescope, and that makes the star images wobble a little bit, and it makes them bigger. So the second graph in that picture is how big the stars are. So if they're really big, it probably was because there was a breeze. So it means I can reject those images there. If you're interested, the images themselves were 2-minute exposures and no filter. So it was pretty basic stuff. But anyway, the analysis was done like that. And this is the point where I step in and I get to reject which ones look bad. Okay. And I can come back if I change my mind, I can always include them. The next bit is how you measure the brightness. So this is called aperture photometry. So in the middle of that picture is the target, T. And what I've got to do next is select some calibration stars, so comparison stars. So these are things which ideally will be fixed brightness through the entire imaging session. So you hopefully don't choose a variable star, something which is like not known to science at the moment. You want stars which don't change so that you can compare the brightness of the target with these fixed brightness stars. And I found 3 comparisons. Okay, so I selected them. You can change things about like the aperture, but all the program does is you decide how big the circle is around the image of each star, and the program converts the pixel brightness into photon counts. And as it changes, if it changes, it will do this very precisely, because your other stars will subject to the same conditions in the image as your target. Everything's going to be measured with respect to the comparison stars. So this is it. I wanted to show you the eureka moment where it happened. So I videoed a replay of it. Okay. So what you're hoping will happen is when you play this, I hope you can see the video. Nothing's happening yet. I'm going to run the photometry. Right, watch this. Let me just explain what you're about to see. This is an image of my target star. It doesn't even look round. When I saw that, I thought, oh, it's not going to work. It's not even round. There's the comparisons 1, 2, and 3. What you want to see is the transit at the top. You want to see the dip, okay? You want to see an eclipse at the top. For the comparison stars, they're being compared to each other as well. You want to see basically flat lines in the others. If there's any variation, it means you chose a variable star accidentally, or one that was new to science that hadn't been known about. You don't want any variation in those at all, okay? So here we go. So the results are coming in. It's going through my images one by one. You think, is there an eclipse? Look at the top one. Look at the top one. Is it changing? I can see no difference in the image of the star at all. Oh, hang on. That's looking like it's dropping a bit there. Yep. Is that dropping? I was punching the air at this time. At this point, I was punching the air. I thought it's like if it goes back up, I'll be happy because it means I've caught it. So have I caught an exoplanet transit? Does it go back up? Does it go back up? There's a bit of scatter in there. So it's going up. It's going up gradually. Yeah, there it is. So I've got a definite dip and a return to normal brightness there. So that was it. That was the kind of, it worked. It worked. So after you do that, the program kind of gets on with figuring out what kind of planet could do that. Okay, so there's a bit of modeling going on. I don't do anything with this. The program just gets on with it. It knows what kind of star the planet is going around. Okay, what it does is tries to figure out the shape of the planet, which gives the best fit to that drop. So it basically randomly generates lots of different possible planets and lots of different possible transits across the star, and it finds the kind of planet which has the best fit to the data. Okay, so it's a process which took a few minutes, but this is essentially the result here. So in the picture, you've got the blue curve, which is the expected based on what we already knew about the planet, and the red one, which is the program's fit to my measurements of the transit, and they're very close. The difference in the timing is about 3 minutes, okay, but the shape is absolutely perfect. The difference in the time, I don't know. It might have been something, and I'm thinking back about it, it might have been the timing of the FITS files when they were created. It might be that there was something to do with the file names, but when I was looking through other people's observations as well, there were similar differences in timing. And also it could genuinely be a difference in timing, that there's an uncertainty with the catalog version of this. And this is my final version of the curve. This has now been accepted onto the ExoClock database. So this is my first official submission of real data. 4,000 odd planets to monitor. Telescopes with professional astronomers, they don't have time to do the follow-ups. They rely on amateurs to do the follow-up work. So there's databases you can feed your work into at this point. So I've got my first observation done. Of course, it's been cloudy since. I haven't been able to do a follow-up yet. Saturday night might look good. We will see. This is what my planet looks like in the middle of the eclipse. The reason it goes down and then back up in a fairly smooth curve is because it doesn't transit exactly across the center. If it went across the middle, you get this, then a drop, then a minimum, and then a climb back up to a peak, and then across. Because it's never completely on the disk, it only ever gradually kind of like dips and rises again. So this is something I looked up after the event, but that's why it's the shape that it is. Okay. Right, so just to summarize, in case you hadn't worked it out, astronomy is fun, but I always read that astronomy was one of the sciences that you could genuinely contribute to if you wanted to, and I think I've shown that you can. It kind of takes a little bit of it takes the skills and knowledge that you maybe already have. If you're doing astrophotography, you can easily transfer this, I think, to this kind of experiment. And it gives you first-hand knowledge of how science is done, how we actually know the universe is expanding. Do we really trust the scientists who say that these things dip? You know, everything's reproducible, everything's verifiable. The eclipse happened on schedule. So yeah, this is like a big deal, I think. Anyway, I'm going to stop talking. Right.